Good morning, students. Today I am going to upload the first video of class 9th, and the topics that we are going to cover today are how to represent an irrational number on number line, which is of chapter 1 of your NCERT book. The second topic is the decimal expansion of real numbers, that is how the real numbers looks like when it converts into a decimal form, and the third one is how we are going to convert a given decimal number into P by Q form. So the topics that we are going to cover today representing irrational number on number line. The second is decimal expansion of real numbers, and the third one is converting a decimal number into P by Q form, where P and Q are integers and Q not equal to 0. So these are the topics that we are going to cover today. So firstly, let's discuss how we are going to represent an irrational number on number line. But before this, we all are knowing that irrational numbers are non-terminating and non-repeating in nature. So if a number is non-terminating, so how we are going to represent that particular number on number line? For that, there are some methods which we are going to learn today, and with the help of those methods we can represent any number on number line. So let's start the first top, that is representing irrational number on number line. So for this we are going to use three methods. We are going to use three methods. The first one, which I am calling, is, I gave it a name, direct method. The second one is given in all book, that is called spiral method. And the third one, which I am again calling, is master method. Again, there are some limitations for these two methods, but using this method we can represent any number on number line. So the limitation of direct method, that it is only applicable when the given number, I am going to give an example, the given number is sum of the square of two integers, like this root 5 is 2 square plus 1 square. But this direct method is not applicable for root 3, for root 7, etc. Wherever there is a sum of square of two integers, this direct method is applicable. Like if we need to find root 13. So root 13 again, 3 square, 2 square. So directly we can represent these numbers on number line. Now spiral method, again there is a limitation of spiral method, and that limitation is that it is not applicable for large numbers, large / decimal number. And the third method, which is called master, I am calling master, is used for any number, can be used for any number. So let's see direct method, then spiral method, and after that at last I am going to discuss this master method. So the direct method, suppose we need to represent under root 10 on number line. So if we see our number line, it's 0, it's 1, it's 2, it's 3, it's 4, it's 5. Now again these all are in units, and that units we are going to decide, because every number on number line, the distance between two numbers is 1 unit. Two integers is 1 unit. It is not centimeter, it is not millimeter, it is not kilometer, it is not meter. That we are going to decide whether the distance is centimeter, millimeter, kilometer, meter. So root 10, as I said, I can write sum of square of two integers. So 3 unit, I will go here, 1, 2, 3. And from here I draw a perpendicular of 1 unit, and then I join. So let's this point A, B, this point as C, join A to C. This AC is AC. We are going to take an arc equal to AC, and we are going to represent this arc. We are going to represent this arc on number line, and this point will give us the value of root 10. This point will give us the value of, that is 3 point something. So this method is only applicable when the given number is sum of the square of two integers. Now if there is another number, we cannot represent that number directly on number line. The second method, which I said, is spiral method. So the second method is spiral method, and that method, let's see. With this method, we actually, while increasing 1 integers, we actually get a spiral shape. That is why this method is called spiral method. And let's see, root 2, root 3, root 4, root 5, root 6, root 7, so on. So 1 unit, 1 unit, this is 90 degree, 1, 1, root 2, again root 2 plus 1 will give me root 3. This is root 3. Now root 3 This is root 4. Again it is 90. From root 4, this will give me root 5. And a curved shape, spiral shape we get as on increasing, and this will also pass this line after some time. So this method is called spiral method, but again as we can see, the limitations is if there is root 35, how we are going to represent this using this method on number line. Root 5, root 6, root 7, root 8, root 9, root 10, root 10, root 35, it's very difficult. So for over above all, there is a method which I am calling is master method. Master method is applicable for any number, even the number is in decimal. So let's see how we are going to represent any number, irrational number on number line using master method. So for this, there are some steps. So what are those steps? Suppose we need to represent under root 7.4 on number line. Now under roots as well as 7.4. So the master method says whatever the number given here, draw a line of this much unit on number line. So the first step says draw a line AB equal to 7.4 units. The second step says extend AB to C by 1 unit. The third step says draw the perpendicular bisector of AC and name it as O. Fourth step says taking O as center and OA is equal to OC as radius, draw a semi-circle. The next step says draw a perpendicular from B to semicircle which intersects it at B. At D. Taking an arc of length BD, cut an arc on number line which intersects AC extended to E. last BD is equal to BE is our required length, that is under root 7.4. Now this whole I am going to draw. First of all, I am going to draw a line AB. This is 7.4 units. I extend this AB to C as I said in my V steps. AB, extend AB to C by 1 unit. Then draw the perpendicular bisector, so that I am going to draw here perpendicular bisector of which intersect it at point O. Taking this OA is equal to OC as radius, draw a semicircle. Then draw a perpendicular from B to semicircle, which intersect the semicircle at D. Taking an arc of length BD, cut an arc which intersect AC extended to E. This BD is equal to BE is our required length, that is 7.4. Now in every question, what is the change we can do is only this length. Every time this will be different. This number will be different. Rest all things will be equal. Nothing, not a single line we are going to change. Everything will be equal. Only draw a line AD equal to, if it is 9.1 then 9.1. If it is 3.7 it is 3.7 and so on. So I hope this will help you. This master method is applicable for every question. So I hope this all will help you to solve the different questions of the different books. Now the second thing which we are going to discuss today is decimal expansion of real numbers. Now what is decimal expansion of real numbers? We know that rational numbers are of two types, terminating in nature and non-terminating and repeating in nature. So the second thing which we are going to discuss today is decimal expansion of real, in fact it is bracket with rational numbers. Now as I said that rational numbers are of two types, terminating and non-terminating. So here also there will be two concepts. The first one says when the denominator is 0 and the second is when the denominator is non-zero. So when the denominator is 0, it means remainder is 0, it means the denominator of those numbers are of a particular type, and when the remainder is not 0, then the denominator of those rational numbers are of a particular type. So let's see what we are going to discuss now. First, when remainder is 0. For these, how directly we find that okay, these numbers are terminating in nature, and what is the decimal expansion of those numbers? So for this, after how many decimal places it will be, or without performing long division, how we are going to say okay, this number is terminating in nature, this number is not terminating, repeating in nature. So when remainder is 0, this is actual terminating number. So the first is when denominator is of the form 2 to the power m. Second, when denominator is of the form 5 to the power n. And the third is when denominator is both 2 to the power m and 5 to the power n. Now, where m and n are integers, and this is also positive integers. And the second is, this is B, when remainder is non-zero, that is non-terminating and repeating numbers. When denominator is non-zero, non-terminating and repeating numbers. So here denominator two and other number. Here denominator 5 and other number, and here denominator 2, 5 5 and other number. So these numbers are non-terminating, repeating in nature, and these type of numbers are terminating nature. So example, for each I am going to write 3 by 8. This is also 2 to the power 3. 7 by 25. 13 by 'These all are examples of terminating numbers, where the denominator is either 2 to the power some number, 5 to the power some integers, or 2 and 5 to the power some integers. Here, other than this number, so I can write any number. 3 by 7. Same I am writing 7 by 30, and here I am writing 13 by 252. any number I can write. So these all are non-terminating, repeating. These all are terminating numbers. The third concept for today's lecture is how we are going to convert a given decimal number in the form P by Q. How we are going to represent a given decimal number in the form P by Q. So let's see the third topic for today. Converting a given decimal number in the form P by Q, where P and Q are integers and Q not equal to 0. So here basically the number which we will see in our exercises in exams are non-terminating, repeating in nature. So those numbers are written in a particular form, and that form is, example I am writing here 2-3 questions, 2.85 pe bar. Second is 0.723 pe bar. So let's see how to write these numbers in a form P by Q. So the basic concept behind this is that the bar means, let's see the first question. This is actually 85, 85, 85 till infinite. Now to solve such question, there is a basic concept behind it, that we assume this number equal to x. And we multiply this x by 10 again and again till we get two different numbers whose decimals, numbers after decimals are equal. Like if we multiply, let's assume this equation 1, so multiply both sides of equation 1 by 10. This will be 10x 28.585858. This is my equation 2. If we see both the equations, the number after decimals are different in both. This is something this is this. So we again multiply both sides of equation 2 by 10. This will be 100x 285.85 and so on. If we see the first and the third equation, the numbers after decimals are same in both. So we subtract from 3. This will give me 100x minus x, 99x, 285 minus 2, 283. Now the number after decimals are same, so we are not going to write anything after this. So x, this number will be 283.99. This is my answer. In the second type, the number is something different with the given first number, and now let's see how to solve this question. So the second is, let x is equal to 7, 2, 3, 2, 3, 2, 3 and so on. If we multiply both sides, so this will give me 10x, 7.232323. This is equation 2. But if we see, the numbers after decimal are different, so multiply again. By 10 of both sides of equation 2. We get 100x, 72.323232. Again, in all the three equations, the number after decimals are different. So we again multiply. We multiply by 10 again and again till the numbers after decimals will be same. So again multiply. This will give me 1000x. And this will be 723.232323 and so on. Now if we compare these two equations, we compare. So 2, 3, 2, 3, 2, 3, 2, 3, 2, 3, 2, 3, subtracting equation 2 from equation 4. 1000 minus 10, 990x. 723 minus 7, 716. No number after decimals, so x is equal to actually 716 upon 990, and this is the answer. I hope this will help you again for representing the numbers, the given decimal number in a form p by q. And that is, so please solve the questions from different books, and you can contact me on my WhatsApp number or through call. So thank you for today.